All right, we're going to go back to here. The last example that we solved, we looked at the spectrum. We also looked at the infrared. And based on those two things, we were able to determine which structure corresponded to that spectrum. So we're going to do the same thing down here. It gives us an empirical formula or molecular formula of C4H10O. It has an IR spectrum shown below. And it has 1, 2, 3, 4 signals. Right. So if it has 4 signals, that typically means that there are 4 sets of protons or 4 different types of protons in that molecule. Now, if we look at the infrared, what we see right away is that there is a big looping stretch right here. Can somebody tell me what that corresponds to at 3939?
I knew that is exactly why I knew he didn't.
Say again. All right, so this is typically, not typically, this is where your alcohol shows up. Right, so that's your alcohol stretch. So we got 4 signals, and one of the functional groups present is an alcohol. So let's go back up to here to our choices. We only have 1 alcohol up here, right? And we said it could be 3 to 4 signals when we first started doing this, based on the fact that the OH proton doesn't always show up, right? It depends on the field strength of the magnet and so on and so forth. So let's take this structure. Let's see if we can match up the protons in that structure to the spectrum. All right, so if we have an OH present and it does show up, it's typically going to show up here, somewhere around 3.8 to 4.2, somewhere in there. So we're going to go ahead and label this as the OH proton. Why is it a singlet if it has 2 neighbors? Anybody? Why is the OH proton a singlet if it has 2 neighbors?
I don't know actually.
So
is it because there's none of the same OH?
If we go back up to the initial example, right, we talked about that. The OH proton, it doesn't couple with neighbors. So you're not going to see a splitting pattern because it doesn't couple. It doesn't experience their magnetic fields, and so you don't get that coupling and that N+1, right? That N+1 rule doesn't apply. OH protons don't split. NH protons don't split. So protons on heteroatoms like OH, NH, SH, like that. So if it's on a heteroatom, they don't couple. right? So that's why it's a singlet, even though it has 2 protons adjacent to it. It's a singlet because if it's on the hydrogen is on what we call a heteroatom, it's not going to couple. All right, so let's go back to that example. So we're going to call that the OH proton. You can see the integration is 1. What does integration tell us? Anybody remember that from last week? I know it's been, well, week before last, because I know we had all week out. Well, what does the integration tell us?
Is that the n equals?
No, integration is different. The n+1 rule is for the number of peaks, like the splitting, how many lines that a peak is split into. Integration tells you the number of hydrogens. Right, so that's an OH, so it's only 1 proton. So that number over the signal, that 1 over the signal, means that this signal is representative of 1 hydrogen. All right, let's go to the next set of protons, and I'm going to try to keep this color coded with the example. So this doublet right here is corresponding to this set of protons right here. Right, and it's at 3.35, somewhere in there. Why is it so far downfield? What causes a proton, a signal for a set of protons to be downfield? What's the term?
The higher energy.
Say that again.
I said, does it have something to do with the higher energy?
No, it's not an energetic issue. It's a electron issue, electronic issue.
Isn't it de-shielding?
It's de-shielding, which means that the amount of electron density around a proton is lessened, and when that happens, the proton becomes more electron poor, which a downfield shift corresponds to. So the fact that these 2 hydrogens right here have an oxygen next door to them, that's causing that downfield shift. So that's where that doublet comes from. And I have it, I'm going to keep it color coded. All right, let's look at the methyl groups. What do you think those are going to be? The CH3 groups that are highlighted in pink. How many lines would that signal be split into? You can jump in, Danielle. This is the n+1 rule. So jump in if you want to. All right, how many lines would that CH3 be? Even if it was only 1 CH3 and it was adjacent to that carbon that had 1 hydrogen on it, what would that signal be?
It just be, what it look like, it's n+1, n+2.
It should be a doublet. Okay, so good. And I agree. And if we look at the spectrum, you can see down here that we do have a doublet somewhere about 0.9, which is what you expect for alkyl protons. Right? And if you look at the integration, it's integrating for 6 protons, which makes sense because before we left, when we went through and found all the non-equivalent hydrogens in this example, what we said was that the CH3s were equivalent. So they're not going to generate separate signals. They're going to both be represented by the same signal. So that signal is here at 0.9, and it's a doublet, which you expect. All right, now let's look at the other proton. How many lines should this signal be split into? it's going to be definitely going to be a multiplet because it has a lot of neighbors. So it's going to be something greater than a pentet. But how many lines would that be split into? How many neighbors does it have for that proton? Now, because the CH3s are equivalent, that only matters when you're looking at that signal. But when you're looking at them in reference to another set of protons or another proton, both CH3s count, if that makes sense. So you have to count both of those methyl groups as neighbors. So how many total neighbors does that proton have that's highlighted in lime or lime green, or whatever that is? Yeah, it's lime green. It looks different on my tablet than it does on the screen.
Isn't it 6 hydrogens?
What about the other ones to the left of it?
Oh boy.
Is that right?
Um,
I mean, they are adjacent, right?
Yeah, they
Mhm.
are. Wait, I thought it was. Oh, okay, I see. It's the carbon that it's attached to, and then you look at the adjacent carbon.
Mm-hmm.
Okay,
So how many total
so
neighbors?
yeah, that's gonna be what, 8?
8
Isn't it
neighbors. So n plus 1 is going to be 9. So that signal for that proton should be split into 9 lines, right? And if we look back at the spectrum, you can see that. That's why I zoomed in on it. These two little outer shoulders matter. So that's 1, 2, 3, 4, 5, 6, 7, and then there are 2 more shoulders out here, 8, 9. It may be kind of hard to see, but they are there. And the reason it has that shape, that symmetrical type shape, is because of that model that I showed you, that Pascal's triangle, right? So that's why it's not just 9 lines, all the same height. Some spin states contribute more than others, so that's why it looks like this. So that's a total of 9 lines, and then you can also see right here the integration is 1. So it's 1 proton, and it's a multiplet, and split into 9 lines. And the reason is because of the 2 methyl groups bordering that proton, as well as the CH2, the methylene that's to the left of it. Right. So that's how we're able to match up the spectra with a structure. Any questions about that? Right. All right, let's do another one. So this one only has 3 signals. And let me show you another part to the infrared too. So there's another peak here that's going to be really prominent, and it's this one. And you can see the stretch is at 1041 reciprocal centimeters. And that is the CO single bond stretch. And over here, that's your alcohol stretch. Because one of the parts of the question asked to pick 2 infrared stretches to match functional groups that are present. So, all right, let's do another one. This, okay, gives us the empirical formula C4H8O2. Infrared shown below. Only 3 signals. So let's go back to our choices. Right? We know that, well, we only got 2 left because we've already done 1 and 3. So it's either 4 or 2. If we look at that NMR, how do we know it's not 2? What types of protons are missing in the NMR to let us know that 2 is not the choice? Let's go back up to here. Actually, I'm gonna copy them both. Or not. So if you look at sample 2, we already picked this out that it's going to have at least 8 signals. That spectrum only has 3 signals. So it definitely can't match. But there's some protons that are in sample 2 that would show up somewhere between 7 and 8. Which protons are those? Anybody?
May you repeat the question, please?
Sure. I was asking, so there's some protons that are going to show up in the NMR for sample 2 between 7 and 8. And I'm asking which protons are those? Because that's the NMR spectrum that we just saw stopped at like 4. Right. So we know it's not going to be number 2 as the choice for that spectrum. It doesn't match. But the fact that there are no protons between 7 and 8 right, those aromatic protons, that's where they show up. So if you don't see that signal, those signals between 7 and 8, then there's no way that could be the spectrum for this compound right here. So it's got to be 4. So just copy that. All right, so you have a singlet, a quartet, and a triplet. And the integration is 3 for that singlet, 2 for the quartet, and then 3 for the triplet. That's enough right there to match the signals up. But we're also going to look at the splitting patterns. So if the integration for that singlet is 3, how many choices do you have? In other words, how many sets contain 3 protons in this molecule?
2.
2. So you have 2 choices. What the giveaway is the splitting pattern, right? If this is the CH3 right here, what should that splitting pattern be? If I write that out, are there any neighbors to those protons? On that oxygen, on the next atom over, does it have any neighbors?
Yeah. So you don't count. You just count the molecules with the hydrogens on them, right? Not the oxygen point count.
Well, oxygen is it's the neighboring atom, but it doesn't have any hydrogens on it. So yeah.
So yes.
So what? So go ahead.
Okay, so the thing about this is the part that gets me. So she has 2 molecules beside it, but those molecules have I guess they have 3 hydrogens. So would it be 6 or just be 2 neighbors?
Think about what this is how we're looking at neighbors. All right. So here, let's say this is a carbon that has hydrogens on it. And this is the signal that I care about right here, these 2 right here. On the next atom, let's say it's a carbon, but it's got all methyl groups on it. There are no hydrogens here. So the signal here will be a singlet. Right? Because if you look at what the neighboring atom, that's what I mean by neighbors, or that's what the number N corresponds to with the N+1 rule. N is going to be 0. because there are no hydrogens on the carbon next door. So if you look back up here, for these protons right here, right, the atom next door is oxygen, but there are no hydrogens there. So N is 0, if that makes sense.
Yeah.
So you're looking at the connectivity. That's why I said, as part of the definition of NMR, what it tells you is the carbon hydrogen framework, because you can tell how atoms are connected based on how the signals are split. If it's a triplet, that means something that has an atom next to it with 2 hydrogens on it. If it's a singlet, that means it has an atom next to it with no hydrogens. If it's a quartet, that means it has an atom next door to it with 3 hydrogens, so on and so forth. So this N is 0, so that's going to be a singlet. So even though we have 2 signals that integrate for 3 protons, we can tell them apart because they don't have the same splitting pattern, and they won't have the same chemical shift, because one of them is going to be further downfield, these because of the oxygen that's next door, and the other one is going to be further upfield.
Okay, I think so. I think I got it. So, so for the milk, if you were to count that, I guess.
Say that one more time. The last thing you said.
The methyl group, if you were to count the methyl group neighbors, would it have those 2 hydrogens, or would it just be 1?
Yeah,
So I
no,
see those.
the one highlighted in green,
Mhm.
it's going to have 2 neighbors.
Okay.
Yeah, so N for this one is going to be 2. N plus 1 is going to be 3, so this is going to be a triplet.
Okay. Okay. I see.
Right? So now you can tell them apart. So we have a singlet and a triplet, both integrating for 3 protons. So the singlet is corresponding to the protons that are highlighted in pink, and it's downfield because they're next door to an oxygen. And then the triplet is going to be the ones highlighted in green. Right, that only leaves one other set of protons to resolve, and that's the CH2. And for that one, right, N is 3. If you look to the left and right, there are 3 protons on that carbon to the right. There are none to the left. So N is 3. N plus 1 is going to be 4. So that's going to be a quartet. And the fact that it's adjacent to a carbonyl means it's going to show up somewhere between 2 and 3. And it does. All right, you look back at the spectrum, it does. It's at 2.4, 2.35. Right, and that's a consequence of it being next door to that carbonyl functional group.
I have a question. Why is the double bonded oxygen not considered a signal?
There are no protons. All we're looking at, this is proton NMR. So all we're looking at is hydrogens.
Oh, okay.
Now you can do oxygen NMR, but what we're studying right now is proton NMR. So if it's not a hydrogen, it's not going to show up in the spectrum. That's a good question. But there are, and I must color code this, there are different types of, I said that at the outset, that you can do different nuclei. You can do oxygen, you can do fluorine, phosphorus, silicon NMR, deuterium NMR. It just depends on what type of nuclei you want to study. Right now, we're just studying the proton nucleus, so the hydrogen nucleus. So that's why only hydrogens show up in the spectrum. All right, if we look in the infrared, what functional groups can we find in the infrared? What should we see? You just mentioned the carbonyl, Danielle. Where is that? Anybody connect? Somebody tell me where that carbonyl stretch is going to show up for a ketone. I'm sorry, for an ester, which is what this is. So that ester stretch is going to show up somewhere here. It's a very distinctive stretch, and it has a specific range where that is going to be. Can somebody tell me that? It's here.
If it's a stretch, oh, there you go. I was just about to say, if it's a stretch, would it be the longest, the tallest?
No, you mixing this up with mass spec.
Okay,
But
right.
but this is it's a medium stretch for carbonyls. And so it's more intense than a weak stretch or a variable stretch, but it is a pretty good size stretch, and you can see it's pretty prominent. So that's what that stretch is right there. And that keep that carbonyl stretch can be anywhere between 17 and 1800 reciprocal centimeters in the infrared. And then of course you also, it's probably buried in here, but the carbon oxygen single bond stretch is here. So that's your carbonyl. This is your CO single bond. And then over here, this is just alkyl stretching, but it's kind of weak. It's not prominent because there are not a lot of alkyl carbons in that molecule. You only have like a 2-carbon chain, I think. Hold up, let me go back. Yeah. So this is alkyl stretching. All right. Questions about that? Other questions? All right, let's do the last one. And then what we're going to do is this will be, we're not going to do those other examples because I want to hit that last section before the last day of class. And it's a bunch of different reactions, and we're going to have to work through that. So I'm not gonna try to finish these spectra because the second part goes more into detail about complex splitting and things like that. And it's just, we just won't have the time to talk about that and finish the last section too. So let's look at the last spectrum. We know that this is the compound that we're looking at. So I'm gonna just copy it. Right? So we got a bunch of signals here. And if you look in the aromatic section, which is again between 7 and 8.5, notice the integration down here is 4 protons. And if you look on the ring, and I'm not going to go through the details because aromatic protons are kind of tricky. And I'd rather spend time working through the examples that we can understand as opposed to working through the aromatics, which can be very, very tricky to understand, and because they do a lot of weird stuff. But why is that why is that section? And again, we got 3 signals down here, right? Potentially 4, because you could have some overlap with this signal. So, but why is it integrating for 4 protons total? Look at the protons on the ring. How many aromatic protons are there on the ring?
Well, there's 6
On the ring.
on the ring 4.
4.
Am I looking at the right thing? Okay.
There are 4 protons on that ring.
Do those two hydrogens don't count?
Which ones on the chain?
Yeah, like I think the ones I think highlighted in gray, those 2.
You mean right here?
Yeah.
Yeah,
Yes.
they count, but they're not aromatic. You
Okay.
understand what I'm saying? The aromatic protons are the ones directly attached to that aromatic ring. So that's why that set of signals integrates for a total of 4 protons. You follow what I'm saying?
Yeah, I just thought that would count because they're it's feel like they're attached to the ring, but is it because they're attached to something else?
Yeah.
Whereas
Yeah,
the ones
they
on
would
the
have to
rings,
be
okay,
they would have to be on this carbon to be considered aromatic.
okay.
But there's nothing there, right? They are a substituent on the ring, but they're not a part of the ring.
Yeah, okay, yeah. See, I always forget it's a carbon right there.
Yeah, so that's why when you integrate the signals down in the aromatic region, the total is 4 protons. Uh-oh, wrong pen. It's 4 protons because those 3 signals combined represent all 4 of those protons. And each proton has its own signal, like I said, but it's hard to resolve. So we don't know which ones are which. So we're just gonna suffice that and just say that there are 4 protons there total. And that's it for that aromatic section. All right, so those are aromatic protons. Those are the ones on the ring. Now here we're gonna, on this chain, we're gonna have 4 signals because each one of these sets of protons is gonna be different. All right, they're all non-equivalent. So you're gonna have a signal for each one. And if you look down here, you see 4 signals, right? And look at the integration. The integration here is 3. This is 2, that's 2, and that's 2. So this, the one that integrates for 3, which set of protons is that? Because the integration tells you how many protons are represented by a signal. So which set of protons should that be? If the integration is 3, that means that signal is representing 3 protons. So which set?
Is that the one the carbon?
The CH3 you mean on the end?
Yes.
Yes, it is. So let's highlight that. So this is the signal for that CH3. And what should it be split into?
It should be a W.
How many neighbors does it have?
No. Oh, sorry. Oh, it has. So would it be 5? No. I guess I'm count those. Count those as single as individual keys. So 3.
Only what's next door to it. The other hydrogens are too far away to couple with it. So it's only going to couple with these right here. So N is going to be 2. That means the N plus 1 will be 3. So it should be a triplet. And you can see that, right? It is a triplet. It's not really symmetrical, but it is a triplet. All right, let's do which other protons should be a triplet? Which other set of protons? Which signal for should also be a triplet?
Those blue, the blue highlighted hydrogens.
The blue ones right here.
Yeah.
So here, N is what? You got 3 to the right, 3 neighbors to the right, and 2 to the left. So N is 5. So that's not going to be a triplet. That's going to be a sextet. Right? And these right here, what would they be? The green ones, dark green ones. Yeah, N is 4, right? You got 2 to the left and 2 to the right. So that's going to be a pentet. And then the gray ones have no neighbors to the right, to the left, and 2 to the right.
So that's the triplet.
This should also be a triplet. The difference in those 2 triplets, or there are two differences. One is the integration. One is integrating for 3, the other one is for 2. But then the other difference is the chemical shift, because that CH2 is closer to the ring, is going to be more de-shielded. That's why it's further downfield. So, and the reason I say that is because these are all ways that you can tell signals apart. Like that's how you distinguish signals, where they're located, what the integration is, and what the splitting pattern is. Like when we first started looking at this, I gave you those 3 basic things that we look at in an NMR to determine what signal corresponds to what proton. Well, it was 4 things: the number of signals, the location of the signals, the splitting pattern, and the integration. Like those 4 things, you can interpret any spectrum based on those. All right, so let's locate them. So this is here's my triplet right here. The other triplet that matches the gray set of protons. And then we got to zoom in on these to see which one is actually a pentet and which one is a sextet. So this is 1, 2, 3, 4, 5, 6 lines. Again, the shape of it is based on Pascal's triangle, which we talked about when we were talking about splitting patterns. So that's why it's shaped like a triangle, right? The 2 outer peaks of that sextet are smaller because that spin state is different. It's not as prominent as the 2 inner peaks. All right. So this is my sextet. So we're gonna color code that. Is gonna be, that's the blue set. So we're gonna make that blue. And then the other is green. All right, questions about that? So again, what we're looking at the same 4 characteristics every time: the number of signals, the location of the signals or the chemical shift, downfield or upfield, the splitting pattern, singlet, doublet, triplet, quartet, pentet, so on and so forth, and integration, how many protons each signal represents. With these 4 things, you can interpret any spectrum. Chemical shift, integration, and splitting pattern. The number of signals tells me how many non-equivalent sets of protons I have. Chemical shift tells me their location, upfield or downfield. Integration tells me how many protons the signal is representing. And then the splitting pattern tells me the connectivity, what it's next door to, how many neighboring protons are around it. All right, any questions about this example? Right, so let's look at the infrared right quick. So you have a bunch of stuff in here. You got all this alkyl stretching. And then buried underneath that, this is why you can't use infrared definitively to determine the structure of a molecule, because buried underneath that is the aromatic stretch, which is right here. Right, so much weaker stretch, but it's buried under the alkyl stretch. So sometimes when those signals overlap, it's very difficult to determine what's what. But you can confirm that both functional groups are present. Right, and this is also alkyl CH stretching. All right, questions about this example or any of the examples that we just worked through? So when you turn this in, you're only going to turn in that part, not the other part, except for the mass spec that we did, because we did work through some mass spec problems on here, but we're not going to work these other NMR examples because we don't have the time to work through them. They're much more complex, and we don't have the time to work through them. All right, any questions about anything?